Hello everyone, welcome to Module 6 of the Essentials of Turbulence class. In Module 6, we are going to be talking about the scales of turbulent motion. We have split this up into multiple parts, and this is the first part where we discuss the scales of turbulent motion. So the contents of this module include a brief introduction about the different length scales, and one of the most important concepts in turbulent flow, which is the energy cascade. We will then go on to discuss some of the seminal theories in turbulence, which are even used to date, the Kolmogorov hypothesis. We will discuss the energy spectrum. We will look at the Kolmogorov hypothesis again in the context of the energy spectrum. We will discuss something called the structure functions and two-point correlations, especially in the context of autocorrelation functions, integral length scales, and Taylor microscales. Okay, so let's get on with it. And the source again for this module is all the notes are from Pope's book. So one of the main characteristics that differentiates turbulent flow and laminar flow is this range of length scales, isn't it? So in turbulent flow, you have a wide range of length scales, multiple. It's not 1, 2, 3, it's multiple length scales. Whereas in laminar flow, you have just one characteristic length scale. So when I say one characteristic length scale, it's important to understand what that means. You could have a range of length scales in laminar flow, except they are of the same order of magnitude as the characteristic length scale. We are not talking about all length scales being exactly 1.0 millimeters or 1.0 centimeters. We are saying that it is of the order of the characteristic length scale. So if the diameter of a jet is 1 centimeter, in a laminar flow, in a laminar jet, all your length scales are of the order of 1 centimeter. So it could be 0.9, it could be 0.8, it could be 1.2, it could be 0.6. But it's not going to be 10 centimeters, or it's not going to be 0.1 or lesser, 0.01 centimeters. That is what I'm talking about. So a characteristic length scale is this large length scale that governs the flow. And what we are saying is that all the length scales in the flow are of that order, are of the order of the characteristic length scale. That is for laminar flow. In a turbulent flow, you have a varying range of length scales. So essentially what you have is, if the flow is turbulent, then you have a varying range of length scales. So let's say your characteristic length scale is somewhere here. Then you have length scales that are that are probably very small and very large, and that are much smaller. So somewhere here. So let me just call it, L1, L2, and L3. Okay, we are going to have proper names for these length scales, but for now, just think of it as L1, L2, L3. L3 is much smaller than L. Is much smaller than L. L1 is probably slightly smaller than L, and L2 is slightly larger than L. So, but L1 and L2 are of the same order of magnitude as L, whereas L3 is probably several orders of magnitude less than L. The fact that you have an L3, you have an additional length scale that is much smaller than the characteristic length scale, is what differentiates turbulent flow from laminar flow. In a laminar flow, you will only have this range. Everything is of the order of L1, L2, and L. Nothing is L3. Whereas in turbulent flow, you have this L3 additional factor. So that is this range of length scales that I'm talking about. And this module spends the entire time talking about these scales of turbulent motion. So let's begin. So we have these turbulent motions ranging from the size of the flow. What do I mean by the size of the flow? It's essentially the characteristic scale, the characteristic length scale of the flow. So for a jet, it is the diameter of the jet. For flow between two plates, like in a channel flow, it is the channel width. For flow over a cylinder, it is the diameter of the cylinder. So that is your size of the flow, the width of the flow. And we are calling that delta. And we are saying that the turbulent flow length scales range from this delta value to much smaller length scales, to much smaller scales. And that is what earlier I was talking about in terms of L3. Now, these scales become smaller and smaller, isn't it? Obviously, the continuum hypothesis is valid, so we are not going down to the molecular scale. I cannot reiterate that enough. We are not going down to the molecular scale because for using the Navier-Stokes equations here, we have to make sure the continuum hypothesis is valid. So our smallest length scale is still orders of magnitude larger than the molecular scale. However, the scales are becoming progressively smaller. The smallest scales are becoming progressively smaller as the Reynolds number is increasing. So what that means is, if I have two different Reynolds numbers, okay, so if I have Reynolds number of say 10 to the 5 versus Reynolds number of 10 to the 10, my L3 for this Reynolds number compared to this L3 for this Reynolds number. As the Reynolds number is increasing, the smallest length scale is getting progressively smaller. So it is much smaller than the L3 for 10 to the 5 Reynolds number. That is what I'm talking about. So the RE of 10 to the 5 is much larger than the smallest length scale of the RE of 10 to the 10. That is what this sentence means. The smaller length scales become progressively smaller as the Reynolds number increases. So now, the idea of the energy cascade. The idea of the energy cascade, which was introduced by Richardson in 1922, the idea was that the kinetic energy enters the turbulence through some kind of a production mechanism. So what does that mean? Production mechanism. If you take a jet, a turbulent jet, the production mechanism is the inflow of the jet. The way the flow comes in through the nozzle and into the domain. You have turbulence entering the domain like that. You have kinetic energy entering the domain like that. That is your production mechanism. If I take a channel flow is coming into the channel. I have turbulence being brought in. I have kinetic energy being brought in from the flow. It's probably coming in from a tank. It is coming into this channel. So I have this, the production mechanism is the turbulence, is the kinetic energy that is being produced as the flow is coming into the channel. If I have flow over a cylinder, I have flow coming in, the kinetic energy is being brought in by the free stream flow. So I have this production mechanism where the energy is coming in, right? And this is happening at the largest length scales of the motion. This is happening at this L, L1, L2, and so on. Then what happens? So as the flow is coming in, into the domain from the nozzle, exiting the nozzle and coming into the domain, what happens? You have velocity gradients that break up the large scales into small scales. You have a breakup of the large scales to the small scales. And as a result, what happens? The energy gets transferred from the large scales to small scales, which break up into further smaller scales. And the energy keeps transferring from the large scales to the smaller scales. This is called the energy cascade. Now, does this continue indefinitely? Of course not. Once you reach the smallest scale where the viscosity plays a role, where the viscosity becomes active, then you have dissipation that takes over. Then the smaller scales dissipate that energy that existed in them into heat. That entire process is what we call the energy cascade. The energy cascade consists of the energy transfer from the larger scales to the smaller scales, which are then dissipated to heat via the mechanism of viscosity. Keep in mind that you have the energy transfer from the larger scales to the smaller scales. So that transfer happens because you have the large scales breaking up into small scales. What breaks these large scales into small scales? It is the velocity gradient. It is the non-linearity. It is the convective transport. It is the turbulent transport. So just to refresh your memory, if I think about the Navier-Stokes equations, so I'm writing this in a shorter format. So ut plus u dot del u, isn't it, is equal to minus 1 over rho del p plus nu del squared u. All of these are vectors. So this right here is the turbulent transport. This is the inertia term. It is this term that is responsible for breaking up the large scales into small scales. The turbulent transport term, the turbulent mixing term, the macro mixing term, convective transport, all mean the same thing. And this viscous term only becomes dominant at the smallest scales, where it completely takes over and dissipates the energy that is existing at the smaller scales into heat. So when we say that this energy is then transferred by inviscid processes, the inertia term is that inviscid process which breaks up the large scales to small scales. And then the energy is dissipated at the smaller scales by viscous action. So that is your energy cascade. This whole picture was developed by Richardson in 1920s. And then later Kolmogorov in the 1940s added to this, quantified this picture by identifying the smallest length scale of turbulence, which is now named after him, which we call the Kolmogorov scale. So that is the smallest length scale of turbulence. And this module really talks about in detail what those hypotheses are. So let's go deeper into the energy cascade. You have a turbulent flow at very high Reynolds number, and it has a characteristic velocity scale u and a characteristic length scale L. So this characteristic velocity scale, just like I was describing the characteristic length scale earlier, is the velocity scale that determines the flow, which means for a jet flow, it is the jet velocity. It is the velocity in the nozzle, average velocity in the nozzle. For a channel flow, it is the velocity, average velocity at which flow comes into the channel. For a flow over a cylinder, it is the free stream velocity. So these are your characteristic velocities, the velocities that determine the characteristics of the flow. And you have a characteristic length scale, which I described earlier. So you can define a Reynolds number based on this. Re is equal to UL over nu, where U is the characteristic velocity scale, L is the characteristic length scale, nu is the kinematic viscosity. So all of this is a characteristic of the flow, meaning you have this information even before you have started the flow, correct? Because you know what your diameter of the nozzle is. You know what the diameter of the nozzle is, so that determines your L. You know what condition you're going to feed in the velocity into the nozzle. Based on the flow rate, you will have the velocity, so that's your characteristic velocity. You know what material you're going to use as a fluid, whether it is water, air, whatnot. So then you know the kinematic viscosity. So this is, so you know your Reynolds number even before you start the flow, isn't it? So that's that. Now, once you start the flow, what starts happening? According to Richardson's view of the energy cascade, turbulence consists of eddies, right? Motions of different sizes, different length scales, so different eddies of different sizes. And let's put some numbers here. Numbers meaning let's put some names here. Eddies of size L have a characteristic velocity u of L. So you have each eddy, let's say, has a length scale defined as L. And then it is associated with a velocity scale, let's call it u, which is obviously a function of L. And correspondingly, you will have a time scale tau of L, which is a function of L, which is L over UL. So you have multiple length scales, right? So each one has a different L. So L1, L2, L3, L4, so on and so forth. So that is why we are saying that U is a function of L and tau is a function of L. L is the length scale of each eddy, each motion. Now what is an eddy? So eddy is conceived to be some kind of a turbulent motion, localized. Okay, so it is local, meaning restricted to a certain spatial location that is at least moderately coherent over the region, meaning it has a definite boundary. It has a definite boundary. So we can say, okay, this is an eddy, like the way I've drawn it here. I've drawn a cartoon here, but like the way I've drawn it here, it has a definite boundary. So that is what we mean by it is coherent over the region. So that's the definition of the eddy. Now, the eddies in the largest size range, we characterize it, let's say we can characterize it by a length scale L0. So this is at the largest length scale. Now this is comparable to L. So this is very similar to what I wrote as L1 here. Okay, here I did say that I've just given some names here as L1, L2, L3, but we'll have more formal names as we go. And that is what I mean by this. So the eddies in the largest size range are characterized by length scale L0, which is comparable to L, which is of the same order of magnitude as the characteristic length scale. Now this L0 is your largest length scale that develops as the flow happens, as the flow occurs, as the flow develops. That is what L0 is. Capital L is some information, it is a characteristic length scale, information of which is available even before you start the flow, isn't it? Like the diameter of the nozzle, like the diameter of the cylinder, like the channel width. But L0 is different. Capital L here, or this fancy L here, is something that you have information about even before you start the flow, whereas small L0 is the largest length scale of the flow. So correspondingly, you will have a U0 associated with the velocity of the largest eddy, and that U0 is a function of L0. That is your velocity scale. So that is your largest velocity scale. And this would be of the order of, so just like L0 is of the order of this fancy L here, U0 would be of the order of square root of turbulent kinetic energy, isn't it? So technically it would be 2/3 K, because K is half times U1 squared plus U2 squared plus U3 squared, the kinetic energy. So what we are saying is that let's assume you have this U prime, 3U prime squared, isn't it? So U prime is 2/3 K to the half. That is what we are saying. So what I did was I just assumed u1, u2, u3 are all the same, and then I can write this as 3u prime squared, isn't it? Order of magnitude. So u prime is 2/3 k. So your large scale velocity, your largest characteristic velocity associated with the largest eddy is of the same order of magnitude as the RMS of the turbulence intensity, which is u prime is 2/3 k to the half. Now again, which is also comparable to the characteristic velocity scale. So there can be a Reynolds number associated with this largest eddy, which will be a local Reynolds number, isn't it? So you have Re0 is U0L0 over nu. And this is therefore large and it is comparable to Re. So here is what you have done. You have this characteristic velocity scale. The largest velocity scale U0, which is of the same order of magnitude as the RMS of the turbulence intensity, is comparable to U. You have a characteristic length scale L. You have the length scale of the largest eddy L0, which is the length scale of the largest eddy, isn't it? Which is comparable to L. So all of this means you can have a corresponding large scale Reynolds number. This is the local Reynolds number associated with the largest eddy. So Re0 is U0L0 over nu. And this is obviously going to be a large value because we are talking about a turbulent flow. If this Re is large, this Re0 is also large because they are of the same order of magnitude, which means the effects of viscosity are negligible at this length scale because the Reynolds number is large. Reynolds number is inertia over viscous. So if this Reynolds number is large, viscous effects are negligible. So that means viscous effects are negligible at these length scales. So that is your context, isn't it? Now that takes us to the Kolmogorov's hypothesis. Richardson's notion was that the large eddies are unstable and they break up into smaller and smaller scales. And what happens as they break up, they transfer the energy from large scales to the small scales. And this is what we call the energy cascade, isn't it? Now, where does this continue till? We kind of alluded to these points in one of the earlier modules. The energy cascade continues until the Reynolds number is sufficiently small that viscous effects takes over. That molecular viscosity is then effective in dissipating the kinetic energy. Okay, let me repeat that. The energy cascade continues until the Reynolds number is sufficiently small. So when the Reynolds number is small, what happens? Reynolds number is inertia over viscous. If the Reynolds number is small, that means the viscous effects are high. That means viscosity takes over at those scales. For what? For dissipating the energy that is left over in those small scales into heat. So if it is dissipating, there will be a rate of dissipation. Let's call that rate of dissipation epsilon, like we have explained it before. The rate of dissipation epsilon is now determined by the transfer of energy from the largest eddies, because that is the first step in this energy cascade. What is the first step? The transfer of energy from the large scales to the small scales. And what we are saying is that the dissipation epsilon is determined by the transfer of energy from the largest of eddies. And it scales, you would think that it scales according to rate of change of kinetic energy, isn't it? Rate of change of kinetic energy. So epsilon would be scaling according to rate of change of kinetic energy. So that is u squared, which is kinetic energy, divided by time, tau 0. And based on that, it would be u0 cube over L0, isn't it? Because since tau 0 is what? u0 over L0. That's the definition of the time scale, velocity divided by length scale. So that is what we mean by that epsilon scales according to u0 cube over L0, which is a simple definition of the rate of dissipation. It scales according to the kinetic energy. the rate at which kinetic energy decreases. This is consistent with experimental observations, indicating that epsilon is independent of mu. So as you can see, when I say that the kinetic rate dissipation, kinetic energy dissipation rate is equal to, or is of the order of magnitude of, as u0 cube over L, u0 cube over L0, it clearly is showing us that it is independent of that viscosity. So that epsilon is determined by the rate at which energy is transferred. That is how we got u0 cube over L0. And it turns out it is independent of viscosity. This is what is happening at the large scales, isn't it? So what we have done here in this class is that we have introduced the energy cascade. We have explained what the energy cascade is, and we are now starting to talk about the Kolmogorov hypothesis. We are starting to build a platform for describing the Kolmogorov hypothesis. The platform is as follows. You have the energy cascade where the energy is transferred from the large scales to the small scales. The large scales are breaking up into smaller and smaller scales. That's the energy cascade. And what we are saying is that there is a dissipation that happens at the small scales. And what we are saying is this is determined by the transfer of energy from the large scales to the small scales, because that is the first step in the process. And so if you just use an order of magnitude analysis for dissipation, epsilon turns out to be equal to u0 cube over L0. And it turns out that it is independent of viscosity. Viscosity is not there in the term. So it is independent of viscosity. So what we are saying is that dissipation rate is independent of that viscosity at these scales. That's what we are saying. So in the next class, what we will do is we will start to describe the first of the Kolmogorov's hypothesis and move on to the second and the third. Thank you.